In our next example for hypothesis tests with population means, we're going to look at a common belief of body temperature. So in 1868, a German physician, Karl Reinhold August Wunderlich, set the human body temperature to be 37 degrees Celsius. And 37 degrees Celsius, if we do the conversion, is 98.6 degrees Fahrenheit. So in the late 19th century, he had done a lot of temperature measurements and saw this repeating value. So he set this value. The problem was in his book and the dictionaries that quoted the averages, they used the word about to show that there's some variance, but they generally didn't state how much that variance was. And so it just became this common belief that the normal body temperature is 98.6. Now, if you really start to study human physiology and you start looking into things, body temperature varies not only from person to person, but with one person throughout the entire day, depending on if they're awake, asleep, doing doing activity, what mood they're in, which is how mood rings work, and also how they're being measured and with what type of measurement tool. So all of these things are contributing to body temperature. An author of a statistics book decided on his own he's going to do a random sample. So he collected temperatures for 106 people, and then we have some sample statistics. The mean 98.2, standard deviation 0.62. And we're going to run a hypothesis test to determine if the population mean is truly 98.6 degrees Fahrenheit. So the two requirements that we have for means, is it a simple random sample, and is the population normally distributed, or is our sample size bigger than 30? So the first one, we have a simple random sample. It says we were using random sampling to collect the temperatures. And then in the second one, we don't have anything about it being a normal distribution, but N is 106, which is definitely greater than 30. So both of our requirements are met. We can now state our hypotheses and identify the claim. So our hypotheses, we have a null and an alternative. We're doing a mean, so we'll use mu. And then we want to test the common belief the population mean is 98.6 degrees. Is means equals in math. So we're going to have equals 98.6. How about for that alternative? Well, we don't know if the mean should be greater than or less than for the alternative. Also, our claim is the null hypothesis, because that's our common belief that we're testing. So our alternative hypothesis, we're going to make not equal to. Now we're going to find the critical value, compute the test value, make the decision. So steps 2, 3, and 4 are taken care of in our template. So we'll pull our template up. I'm going to delete the data from our previous problem. We're using a 0.05 significance level, so I'll leave the 0.05 in there. This time our alternative is not equal to. So we'll make sure to change that symbol, and it's not equal to 98.6. Delete all of those. There we go. Clear it all out. And now we're going to put in our sample statistics. So sample statistics that are given, 98.2, 0.62, and our sample size was 106. And we put those in. We have our t-value 1.98. We have our test statistic negative 6.64. We have a p-value with this e in it. Do you remember what the e means? It's a very, very small probability. And then we have our conclusion that tells us to reject the null hypothesis. So we'll talk through that. I grabbed a snapshot of our template and some important values that we're going to pull out. We'll highlight them in pink. The critical value, 1.983. Our test statistic, negative 6.64. And I will point out that this t-value is actually plus or minus because it's a two-tailed test. It'll be plus or minus. And then our p-value here. And then notice it says to reject the null. So those are the pieces we're going to pull from, put them into our hypothesis test over here and talk through them. Okay? All right. Our critical value is plus or minus 1.9828, 1.983. And if we draw our t-distribution here, we're going to have a 1.983 and a negative 1.983, and our rejection region in the tails. And then computing the test value, or the test statistic, we use those words fairly interchangeably, that was the negative 6.642. So scrolling back over here to show it, here's our test statistic, negative 6.642. And then p-value, the funky number with the e in it, we'll write that down in a minute. So using the test value and the critical value, we can do the traditional method right now. So the traditional method says take the test statistic and put it on the number line relative to the critical values. So negative 6.642 is going to be even farther than where I'm putting it right now. But remember, it's relative. It doesn't matter the actual distance. It just matters what side of the critical value it's on. And we have the test value happening in the rejection region, which means we are going to reject the null. It's in the rejection region, we reject the null. If we're doing the p-value method, remember, you only need to do one, but I'm showing you both so that you can see both. If we're doing the p-value method, the p-value that we are given in the template, 1.40369, 1.404 e to the negative 9, 1.404 times 10 to the negative 9, which means we basically have 8 zeros and then a 1. So we're taking the decimal point that sits between the 1 and the 4 and we're moving it 9 spots and filling in the zeros. We're comparing this number to alpha, which is 0.05, and we see this. The alpha is much bigger. So this probability being so small, it's not likely to happen at all. Not likely to happen by chance. And since it's not likely to happen by chance, then the null hypothesis must not be true, or it's very unlikely that it's true. And since it's very unlikely that it's true, we would end up rejecting the null, just like the traditional method gives us that result. So we'll end up with the same result no matter what. This p-value that the template gives you is actually twice the area. So it's both sides of the area that's related to the negative 6.642. So let me write it this way. So looking at this, we've got negative 6.6 and positive 6.6. It's talking about 6 standard deviations away from the mean. 6 standard deviations away. That's really far away from the mean. 6.6 standard deviations away from the mean. And so this 1.404 times 10 to the negative 9 is talking about both of those areas together, both tails together. So now that we've got that, make the decision. We're rejecting the null, reject the null hypothesis, and you can either write it as reject HO or reject the null. If you want to write it out instead of symbols, you can absolutely write that. And now we're going to summarize the results. So we had the claim that the population mean is 98.6 degrees. We just rejected that claim. So we would say there is evidence to reject the claim that the population mean temperature is 98.6 degrees Fahrenheit. Now notice the use of rejecting the claim in this problem compared to supporting the claim in the last problem. In referring to that, I'm going to bring us back to 8.1. When we're wording our conclusion, if the claim is the null, which is what we have for this particular problem, and we rejected the null, which is what we had, we would say there is enough evidence to reject the claim. Anytime our claim is the null, we're talking about rejecting the claim. And this is because the null is representing one single value out of a continuum of values, infinity values. We can't support a single value being true out of infinity values. This is where a little bit of math comes in. The probability of that single value out of an infinity of values is 0. So we can't support a single value. But if our claim is the alternative, then we can support the claim because our alternative is talking about being less than or greater than or not equal to. So that inequality gives us more values than just one to work with. So when you're working with your conclusions and trying to word them, if the claim is our alternative hypothesis, which is an inequality, we either have enough evidence to support the claim or we don't, depending on how our decision comes out. If our claim is the null hypothesis, then we have enough evidence to reject the claim or we don't, depending on our decision. So the table might be a little handy in wrapping your head around how we should be concluding these types of problems. So refer back to your notes when you're working through the problems until you get used to the lingo. It actually turns out that with these studies, the acceptable range of, quote, normal human body temperature is actually between 97.7 and 98.6 degrees Fahrenheit. And again, we're talking about it's dependent on individuals and the time of day and all of these other factors, but in general, we have a range of values instead of just sticking with this one value of 98.6 degrees.